Now, what if I have a case when I cannot really derive a mathematical model for the system, but for a specific system I was able to, through experiments, measure a time history of the response of the system x of t as a function of time, experimental measurements. So, how can I derive a form of the response, derive the parameters of the response using this graphical history? Let's see, first, I can easily determine the period of the response. Let's say this is the first peak at T1 and the second peak at T2. Then I know that the period of the response, of course, notice that this is a damped response, so the system is under damped, and the period will be the damped period. T will be tau damped, which is T2 minus T1. And of course, knowing what the period is, I can determine the frequency, which is 2 pi over the period tau t. And that's a simple way to find these two parameters. The not straightforward part is finding the damping ratio. What is zeta? And this is an important parameter in damped systems. So, how can I do that? Let me first assume that the response x of t is some amplitude x e to the power negative zeta omega n t sine omega d t plus some phase angle phi. So now if I find the amplitude at T1, x1 at time T1 will be x e to the power negative zeta omega n T1 sine omega d T1 plus phi. And x at time T2 is x e to the power negative zeta omega n T2 sine omega d T2 plus phi. Now, T2 is T1 plus tau d, the period, or the damped period, which is, if I substitute here, I'll get e to negative zeta omega n T1 plus tau d sine omega d T1 plus tau d plus phi. Now, this power is the sum of two values, so I can convert it to the multiplication of two exponents. So this becomes x e to the power negative zeta omega n T1 times e to the power negative zeta omega n tau d sine omega d t1 plus phi plus omega d tau d. Now, tau d, and here is 2 pi divided by omega d. So I will have x e to the power negative zeta omega n t1 e to the power negative zeta 2 pi omega n divided by omega d sine omega d t1 plus phi plus 2 pi. You substitute tau d 2 pi over omega d. Now the sine of an angle plus 2 pi is the same as the sine of the angle itself. So I can rewrite this as x e negative zeta omega n t1 e negative zeta 2 pi omega n divided by omega d sine omega d t1 plus phi. Now I will divide x1 by x2. Of course, x1 and x2 can be determined from this graphical representation of the time history of the response x of t as measured experimentally. So dividing x1 by x2, most of the terms will cancel. X and this exponential term, the sine term, and I will end up with only 1 divided by e to the power negative 2 pi zeta omega n divided by omega d, which is e to the power 2 pi zeta omega n divided by omega d. But recall that omega d is omega n square root of 1 minus zeta squared, so that will also cancel omega n, and I will end up with e to the power 2 pi zeta divided by square root of 1 minus zeta squared. Now, taking the natural logarithm of both sides, then x1 divided by x2 will be 2 pi zeta divided by 1 minus zeta squared, and we'll call this delta, which is called the logarithmic decrement. Now, so measuring x1 and x2 experimentally, I can substitute and find delta and then solve for zeta using this relationship. So I can also write this as in general form as len. If this is xi, then here will be xi plus 1 equals delta, or xi divided by xi plus 1 is e to the power delta. Now, for more or better accuracy, sometimes you want to take more than one peak to eliminate errors due to measurement. So instead of taking x1 and x2, I might want to take x1 and x5, for example. So if I use x1 and x1 plus m, I can expand this as series of fractions, x1 divided by x2 times x2 divided by x3, x3 divided by x4, and so on until xm divided by xm plus 1. Now, x1 divided by x2 is e to the power delta. So each two consecutive peaks will give me e to the power delta. So 2 and 3 will also e to the power delta, e to the power delta for 3 and 4, all the way to xm, multiplying, that will be e to the power m delta. So now, if I take the logarithm of both sides, x1 divided by x1 plus m will equal to m delta, or delta is 1 over m ln x1 divided by x1 plus m, or in its most general form, delta is 1 over m ln some xi and xi plus m. So if I take two peaks separated by m number of periods, I can determine a more accurate estimate of the logarithmic decrement delta, and then substituting this delta to this relationship, I can find zeta, which is the damping ratio in the system. So, in summary, from this history, I can find the period, I can find the frequency, damped period and damped frequency, and using the logarithmic decrement from the number of peaks on the response, I can find zeta, and of course, if I know omega d and zeta, I can find omega n, and using all these parameters, I can write the response of the system x of t as some constant x e to negative zeta omega n t times sine omega d t plus phi. Zeta is known now, omega n, omega d v, that's all I need, and the x and phi can be determined by the initial conditions. Or I can substitute T1 here and find X1, and then substitute T2 and find X2, and from the two relations, X1 equals this function at T1 and X2 the same function at T2, I can solve for the amplitude X and the phase angle